Welcome back to Lecture 2 in the Galaxies course Fall 2025 at Stockholm University. This is the second part of the lecture. In this part, we are going to look at galaxy classification, and in the third part, we will take a closer look at galaxy morphology. These two topics are overlapping and intertwined, so this separation will not be complete, but these are going to be the main focuses of these two lectures. Morphology means the study of the shape of things, and the classification scheme that we're using for galaxy classification is largely morphology based. So this is a look at the Hubble tuning fork classification scheme, or actually, as you can see, it's called the Hubble Devaucouleur diagram. In the original Hubble tuning fork scheme, there were only two arms. The one up here showing the usual normal spirals, and the one down here showing the barred spirals. In the Devaucouleur diagram, there's also the intermediate spirals here in the middle. The galaxy types E0 to E7 are called ellipticals, and there are also the so-called lenticular galaxies over in this arm of the tuning fork diagram. These are called early type galaxies, which is a little bit of a misnomer and a little bit misleading, but for historical reasons, we still cling on to it. They were called early type galaxies because originally people interpreted this sequence here as an evolutionary sequence where galaxies started out in their simplest possible shape and then grew into more and more complex shapes over time. However, this is not how things actually work. And even Hubble himself, at some point, cautioned people against interpreting the Hubble diagram as an evolutionary sequence. But the terminology and early type and late type galaxies, for some reason, still sticks for historical reasons. As you can see, the lenticular galaxies, as you can see, the elliptical galaxies have numbers from 0 to 7. These numbers are simply a measure of how stretched, how elliptical they are. It is basically a measure of the ratio between their minor and major axes, with E0 having 0 ellipticity and E7 having the maximum ellipticity. In principle, one could go even further, but we do not really observe galaxies with an ellipticity beyond E7. In the other side of the diagram, we have the star-forming galaxies. These are spiral galaxies, and they are irregulars. As I said before, if we look at the spiral galaxies, these have in one arm, the barred spirals. Up here, the normal spirals, also called unbarred, and the barred spirals down here with some kind of intermediate spirals in the middle. In reality, the entire space here is populated with some kind of, you could say, some kind of continuous change from no bar at all to very strong bar. From the A, B, C, and D out, these are measures of how tightly wound the spiral arms are. So you can see in A, we start with tightly wound spiral arms, and out in the D, you see that we have completely loosely wound spiral arms. Then we also have these ones here, which basically means they are irregular, but with some semblance of spiral shape still. And out here, we then have the completely irregular galaxies. And again, we caution that this is not actually an evolutionary sequence, at least not in a way that this is useful for. So let's go through the different galaxy types. If we start with the elliptical galaxies, the E0 to E7, we see that these galaxies are round and smooth and largely featureless. These contain, so they have very little no spiral arms and very little dust lanes. We used to say no dust lanes. That is not actually true, but compared to spiral galaxies, the dust features are very faint, very weak. These galaxies also have very little cool gas, but they are very rich in hot gas. There are normally no emission lines in their spectra, or only very weak emission lines. They have a quite red stellar population. And if you can think about for a bit what that means about the stellar population's physical properties, take a little moment to do that now. They also have no or very few young massive stars in them, basically no star formation at all. And again, E0 are spherical and E9 are extremely elongated. And as I said, we rarely classify galaxies beyond E7. Bright ellipticals mainly live in strong overdensities or galaxy clusters. Elliptical CD galaxies are the most massive galaxies we know of and form the centers of galaxy clusters. They are also usually called brightest cluster galaxies or BCGs, but they are often of type CD. And these galaxies are special and different from the other elliptical galaxies for reasons that we shall return to in a later lecture. Here's an example. Say that this galaxy M87, again, one of the Messier comet imposter nebulae, is an E0, so it's basically completely isotropic with no ellipticity at all. It is also a CD galaxy, a brightest cluster galaxy, which makes it special in multiple ways. If we zoom in, we can see that there is this jet coming out of the center of it. M87 is the host of the supermassive black hole that was imaged in radio waves by the Event Horizon Telescope as the first directly imaged black hole ever a few years back. And what we see here is a jet that is protruding, being ejected with very, very high speed, very high velocity from this supermassive black hole. A supermassive black hole that is, if I remember correctly, around 9 billion solar masses in mass. So quite extreme. This is an example of an E2 galaxy. We can see a little bit of elongation in this one. This one is M60, so another one from the Messier catalog. Normal or giant ellipticals are usually somewhat brighter than spirals or galaxies like the Milky Way on average. They often have low, large-scale rotational velocity. So instead of having ordered rotation, their stars are moving around in seemingly almost random orbits. So in a way, one could say that they are something resembling pressure supported rather than rotation supported. Fainter ellipticals show more rotation and can even have faint disks, which can make them a kind of an intermediate form of galaxy between these and lenticulars, which in their turn, again, can be seen as some intermediate step between ellipticals and spiral galaxies, but we will get back to that. The faintest ellipticals are called dwarf ellipticals and dwarf spheroidals. So they have this little D in front of their name, here and here. And again, elliptical galaxies are far, far more common in dense environments such as large galaxy clusters and so on. It is quite rare to see an elliptical galaxy in the field far away from other galaxies. Here's a dwarf elliptical called M110, just to show another example of different variety of ellipticals that exist. Lenticular galaxies have thin rotating disks of stars, but these stars are red and they're old. And like elliptical galaxies, lenticular galaxies also have very little gas or dust. Lenticular galaxies are also common in dense environments, but they, as you can see, still kind of sort of resemble disk and spiral galaxies, except they are not as well ordered as disk and spiral galaxies. They have no gas or dust, but they do retain some kind of spiral-like structure. They may even have a central bar. This is a hint, of course, that lenticular galaxies might be a later evolutionary step of spiral galaxies at a point where these spiral galaxies have largely lost their cold gas and their dust. If we take a closer look at spiral galaxies, again, here is the Hubble tuning fork diagram from before, but without the central arm from the de Vaucouleurs diagram. And we see again that we have the spiral A to C. Some people also operate with a D and onwards. And what we see is that these galaxies are having bright blue spiral arms with clumps of hot OMB stars in them. They also contain dust and cold gas from star-forming regions. There's lots of star formation happening in spiral galaxies. And finally, about 50% of them show a central bar. If we look along the sequence from S0 and out to SC, and from SB0 and out to SBC, we see that from SA and SBA, they are have tightly wound spiral arms, and they have a very pronounced, large, strong central bulge, this thing you see here and here. As we move out the sequence, the spiral arms get less tightly wound, and as we can see, particularly here and here, the central bulge becomes less and less dominant, less and less pronounced. You may remember this galaxy from the last lecture. This is M51, which is it has a long, complex categorization, because since the Hubble classification scheme was made, of course, people have refined it and made a bunch of under subclasses and so on. But it is an SAB, SAC galaxy. And it's also called a peculiar galaxy because, as you can see here, it is interacting with a companion galaxy, which makes it a little bit strange. This is imaging with the Hubble Space Telescope. And as you can see, I think this is a very, very beautiful example that we have these spiral arms of stars, and we have these dust lanes that follow the spiral arms. And finally, we have these red dots here, which is glowing interstellar ionized gas, marking regions of intense star formation. So we have these star-forming regions that kind of sit at the edge or inside the spiral arms, and then we have the light from the blue stellar population that has recently formed also in the spiral arms in adjacent regions. It's important to note, though, that even though we see the most starlight, especially in blue and optical light, in the spiral arms, it doesn't actually mean that most of the stars are found in the spiral arms. But the stars that we find in the rooms in between the arms, in the inter-arm space, are older because they have not formed there. So the young stars and the most massive stars that give the strongest and bluest light, they live shorter, as we found out last time. And that means that they do not have time to disperse very far from the spiral arm before they reach the end of their life cycle. In contrast, smaller stars that live longer will have a much longer time to disperse into the disk and form a smooth disk, kind of underlying the spiral arms that we see. But those stars are much less bright, especially in optical light, than the young stars are, so we don't see them very well in observations like these.